just check. Okay. Welcome everyone to week 3 of the PMRF TA sessions for this NPTEL course, Electronic Properties of the Materials Computational Approach. A brief introduction of mine. I am Akshay. I am a PhD student PMRF in the Solid State and Structure Chemistry Unit, SSCU of the Indian Institute of Science, ISC Bengaluru, India. I did my BTech MTech dual degree from IIT Kanpur in the Department of Materials Science and Engineering, and I am an NPTEL-PMRF TA for this course. And we will have in total 8 2-hour interactive problem solving sessions that we are having on every Friday from 7 p.m. to 9 p.m. during the run of this course. Alright, and in today's session, so what we will do is we will start with the problem of infinite square wave in the case of symmetric potential, and go to the Python script for that, which we were not able to do in the last session. And then we will solve some problems on the Sommerfeld free electron model, and then we will go through the Python scripts of the lecture and check, because the scripts were discussed only for the 3D case, so I will try to discuss some of the script for the 2D case, but I just realized but because the week 3 assignment also has some problem in it, so that will be this time the Python script discussion will be a brief one, and in the next session, which will be the week 4 one, we will do a detailed discussion of of these Python script, which will also include solving a question which has been asked in this week's assignment as well. So that's why I will not discuss those Python script in detail. Instead, what we will do is we will do some more problems on the infinite potential, which we missed in the last session. So we will do, after a brief discussion on the Python script which we discussed in the lecture, and then we will go back to theory and do some of the problems for infinite potential. Alright, so let me just go to this. Okay. Alright. Okay. Alright, so this I had discussed in my last session as well, in the week 2 session as well. So in this one, let us just quickly go through what it was. So basically, what we have we know what infinite potential square well is. Now what we have in this case, in the symmetric potential, what we had is that instead of having our well from 0 to a, we have our well from minus a by 2 to a by 2. Alright, so our potential is 0 in this range from minus a by 2 a by 2, which is mod of x less than a by 2, and it is infinite for mod of x greater than a by 2 in those two regions. And then this is that if we use the time dependent Schrodinger equation, and if we use our boundary conditions, then this is the similar solution. So this has been discussed in the previous session as well, so I am just going through really quickly over this. But okay, so it is similar to what we saw. So we get minus 2me by h square, and we get minus k square, and we have k equals to this. Then we can take our trial solution, e to the power iota kx or e to the power minus iota kx, and then our general solution will be this. And now for specific solution, we will apply our boundary conditions, which will give us these values, these conditions, and then using this 1 and 2, we can get this relation e to the power 2 iota ka, that has to be equals to 1. So 2k will be equals to 2 n pi, and thus k will be equals to n pi by, where n belongs to integers. And then our en values, which are h square k square by 2m, they could be written like this, as similar to our previous case of infinite square wave from 0 to a. Alright, and then here a brief discussion, like, okay, we can't have n equals to 0, because in that case our psi of x will be equals to 0 for n equals to 0, and that is not possible for mod of x less than a by 2. So particle must exist somewhere. So this you can check that for n equals to 0, your priority wave function will be 0, and then using our result from 2. Okay, yeah, this condition 2 and the value of k that we have, so we will just put the value of k is equals to n pi by a here, and then we will get a equals to minus p times cos n pi plus iota sin n pi. So we got that A is equals to minus B for even n and is B for odd n. So basically using this we get psi x true solution for even n's and odd n's. Then we did the normalization, and from normalization we got our A value as well, which was as for even and odd n. We take the normalization constant such that our wave functions are real. So accordingly we took this. So this has been discussed in the last session, so I'm just going through it. You can go through that last session video to check in detail. But basically from this we can get our normalization constant. We will use the normalization constant, which will give us the real wave functions. And then so going through all this we get our wave function. So we get that for even and now instead of in case of a symmetric potential, as we know, our solution will be either even or odd. So we are getting some even solution and some and some different like some sine function for the even solution, even and for the odd n we are getting this cos function, and our energy eigenvalues are just the same. That just shows that the physics is more or less the same. And then we can also see the time evolution of the superposition of two energy eigenstates, which will be similar, and this has been done in the previous session. We have done a question also where we derived this equation. So that could that is the same thing. So now we will go to the Python script that was not discussed in the last session. Stop sharing. Okay, let me just start sharing my screen, and we will go to particle and pause symmetric potential. Alright, I hope this is visible. I think, yeah, this is visible. Let me just check once. This thing is visible. Yeah, it is visible. Alright. Alright, so let's go through this. So we first what we are going to do, we are going to import the libraries. Sorry about that. So we are importing our NumPy library, our matplotlib.pyplot from that we are importing, and then we import from scipy, we import scipy.integrate. So what we have done here is that first we define the physical parameters for our problem. So here the width of the well I have taken it to be equals to pi and p dot pi. So our a value, which is, so our well is from minus a by 2 to a by 2, and I have taken this to be pi. And then we have our h bar reduced Planck constant in the equation that I am going to take as 1. Then the mass of the particle I have also taken as 1, and then we have as our wave function minus outside the well. So we are taking the x range values from minus a by 2 to a by 2, and I am taking 5000 values from in this range. So you can do this equation. You can change the value of a and see how the answers will change. Then function, and then this is the function to determine the energy eigenvalue of eigenstate n. So this is defined as, we have the energy n comma a is given by h as we know it is just h bar square times pi square. Alright, it is h pi square pi square n square divided by 2. So we know it is n square h pi we have just seen that it is n square pi, it was n square pi square h pi square. 1 minute. Okay, the energy values are n square pi square h pi square. So that is what we are doing here. We have n square pi square h pi square by 2ma square. Alright, and then we will return this energy value E. Okay, so that is what our function will do. Alright, and then so this is so let me just run. Okay, yeah, let me just run all of these cells. So let me just first import the libraries. Then defining the physical parameters of problem, and then we have this determining the energy eigenvalue of eigenstate. Alright, then we go to first we have to determine the wave function. Okay, now next function is where we are defining our wave function of eigenstate n. Now this function, this takes the value of n, whatever our quantum number is, and then this is the width, what is the value of a of our width of the wall, and it is n is a label of eigenstate n, or you can say a quantum number, or and x is the position value that we, so these three things it takes. Then if in the code, if your n value that you are given that is exactly equals to 0, then this does raise an exception that n must be non-integer. So using this raise function you can give some exception. Okay, so like if some input is wrong, okay, so you can provide a condition and you find that okay, this input could not be there, then you can just raise exception, and then the program will stop and will show this kind of error. Yeah, I will give this value 0 and show you like how this raise command works. Then in this if else loop, if else condition statement, also I have a condition for n less than 0 in case if the user of this code, like if you give a negative integer value, then we know that doesn't make any difference, but just to keep the program same, we will just convert it to positive value, minus 1 times n. Alright, and then this conditional statement, this check whether it is an even n is even or odd. So if n%2 is exactly equals to 0, it means n is even, and then we use our even solution, which is under root 2 by a sine of n pi x by a. Alright, and else if it is not even, so it must be odd, and thus we will have this, and then the function returns our wave function, whatever the wave function is. So this is the function to determine our wave function of our eigenstate n. Then we have a function to determine the derivative of the wave function of this. So okay, so this derivative will be useful when we calculate the expectation value of the momentum. As you know, the momentum operator minus iota h cos del by del x. So when you will find the momentum value, then you have to take the derivative of your wave function. So this function will help you to determine this derivative, and we have both derivative del by del x and del square by del x. So here the code is similar to what wave function is, and then you can just take the square. We know the form of wave function, so then we can just take the differentiation with respect to s, and this is the functional form. So I have just written this functional form here, and same is for the del square case as well. Alright, so similar to the wave function, since we know the analytical functional form of this derivative of this wave function as well, so we can just write it down similar to what we have done for the wave function. Then next is, okay, again I made a mistake. You have to run each cell each time. I am not running this cell. Alright, so this is the wave function. Let me run this cell as well. So this is for the function determine the derivatives of the wave function. Alright, then we have function determine the uncertainty in position of eigenstate n. So this function determine the uncertainty. Alright, so that is our delta x. So we know, so what it does is first it find the expectation value, and we know the expectation value for in case of x is just x times psi times psi. Alright, so then it also print the expectation value for us. Then to find the expectation value of the x square. So this function find the expectation value of the x square. It is just x square times psi and psi, and we are integrating using this dot trapezoidal method. And then we find the delta of x. Okay, this delta of x, as we know, it is just the expectation value of x square minus expectation value of x square. So that is our delta of x, and then this function returns our delta of x value. Alright, so this gives us the uncertainty in the x. Alright, then we have the function to determine the uncertainty in momentum. So for this we have to use this functionality of Python. So in Python it is possible, within Python itself you can define the complex numbers. So you don't need even any library for this. So here I have defined the a variable called iota, which is the square root of -1. So this complex number, it could be defined like this, or you can define iota equals to complex 0, 1, where the real part is 0 and the complex and the imaginary part is 1. So I am using this method. So I have defined iota here, and then we know that the expectation value of momentum is minus iota h cross, and then within the integral you will have psi times del psi by del x, right? So that is what we have written here, and then this prints the expectation value of this of momentum. And then for the del square, to find the expectation value of p square, so then we will have minus h bar square, and then we will have this integration psi times d2 by double derivative of our wave function. And okay, so this value, so this function gets this function actually it requires these two values, so we have to provide it these two derivative function, and then this will also give us the uncertainty in momentum. Alright, so let's go to the wave function and probability density plots. Okay, so this code this plots the wave function and the probability density plot. So first it asks for the index of the eigenfunction, and will be the index of our eigenfunction. Then it calculates the wave function using our wave function the function that we have defined to determine this wave function or eigenstate. So it calculates that. Then we calculate the psi square, which is our probability density. Okay, and probability density, since our wave function is here, is just the psi square. So you can just multiply this psi times psi. Then we plot our wave function and our probability distribution function as well. So what we will have is we will have this num equals to 1. I have not written why I have wave function and alright, and so basically we have this x-axis. We have in x-axis we have just defined this is our figure, and this is PLT dot figure you can define, and you can define this dpi value as well. Then x limit we are taking minus a by 2 to a by 2, and this is how you can define the x ticks. So you can use this. So I am saying that from minus a by 2 0 and a by 2 you have to put minus a by 2 0 and a by 2. So you can like in Python, if you don't provide the text, it will just write a text on its own, whatever the values are, or you can give your give this text manually as well. Alright, and then we will have our this PLT y limit I have taken minus 1.5, 1.5, PLT y text these are the text value minus 101, and I am not giving any value, so I just want only this text to be there, and the value will be Python standard value will be the same, minus 101. And then we are plotting our wave function here. Alright, and with blue color, and the red color we are plotting probability density, and this is just a line for the comparison. Alright, so let's just do it. Alright, so let me give a wave function with n equals to 1. So yeah, so we are getting our n equals to 1. So here we can see that the wave function psi of x, it doesn't have any node, and this red one, this is our mod of psi square. Okay, we can rerun this code. So let's say n equals to 2, and here we can see it is for n equals to 2, and we are seeing a single node. So there is one node here. Okay, and it is at the center, and because of this node you can see that the probability distribution also, it is highest as this between 0 to a by, minus a by 2 0 to a by 2, as since we have the maximum of our wave function as well here. Basically we have this this kind of chain where the del square, basically you can say the saddle points are. So there we have the maxima, and where this psi of x is equals to 0, then there we have 0 probability to find our wave function. Alright, and let me just show you okay what happens if I have, so if you remember in our wave function command we have given that if the input is 0, then it will raise an exception, because that we could not use as a reference, so it has stopped the code. And if you see, the exception has there, so it has raised an exception that n must be a non-zero integer. So we can define this exception using that raise command we can define whatever exception we want to raise. Okay, so this raise exception we can raise whatever exception we want, right? And this is showing the user that n must be a non-zero integer. You can't put a zero value here. Alright. Okay. So let's just go to some images. Maybe just plot. Let's say plot for 3 as well. And then again we are having this. Okay, the blue curve is having 2 nodes, and on this now we have 0 probability, and we are having 3 ups. Okay. Now let's go to the next part. Now in the next part, what we have to calculate the energy eigenvalues. So again we are inputting the index of the eigenfunction, then we are calculating our wave function, whatever our wave function is, and way to calculate the energy of the eigenfunction we can calculate here. Okay, that is just n comma a, and then we are printing our energy value. Then we are also calculating the position uncertainty. Now to determine the position uncertainty, we have to give this wave function times x, and that will give us the position uncertainty. Then we also need to find the momentum uncertainty. For momentum uncertainty, we need this first derivative and second, both we need both the first and second derivative of our wave function. So we are giving it by this using the function that we have defined earlier, and then this gives you delta p, where we just go to that function and give the uncertainty function, and it gives the momentum uncertainty momentum here. And then this part of code, it checks whether the Heisenberg uncertainty principle is valid or not. If it's not valid, like we are doing something extremely wrong. So like here it is going to product of this, so it just stated delta x times delta p, and just check that the product is greater than equals to h bar by 2, and if it is, then uncertainty principle is validated, or if it is not, then something is very wrong. Heisenberg is unhappy. Hopefully like we will never get this kind of comment. If this conditional statement done, then we have done something really wrong in defining our problem. Alright, so let's go to 1. So for n equals to 1, it has given us the energy eigenstate. It is giving a 0.5 value, so that you can check according to the parameter that we have taken. Expectation value of x is 0, so expected, like for 1, our expectation value of x is in the middle of the box, and as we know that probability density, if you also remember, that probability density was also maximum at middle only for n equals to 1, and thus the expectation value of x is also there. Of x is we are also getting similar 0 value, so most of the time, because there was the higher probability as well. Then this is about position uncertainty. Expectation value of momentum is also 0. J it is writing because it is a complex number, but it is basically 0, and the momentum uncertainty is 1, and thus this is validated. Okay, we can now check this thing for 2, n equals to 2. Again we are taking 0 value. Again the momentum and the expectation value are the same. The uncertainty principle is still validated, and okay, I should have taken 4.5. Here you can see that for 1 it was 0.5, and we know that it goes by n square, so the next value will be 4 times of this. This is 4 times of this, and it will be 9 times of half. It is like 4.5, I guess, so it should be, I guess, it is 4.5. Energy state is 4.5, and everything else is also validated. Momentum we can get, okay, we have seen that, okay, momentum expectation value of momentum, it might it is coming in this value, and the uncertainty is here. So you can check it for different eigenstate function, and we can see that uncertainty principle is still being validated. Alright, and let us go to plot. here you can see that, okay, here you can still see that, okay, there is some value for n equals to 3. I just got comment, but it is 10 to the power minus 6, so it is still 0. So our expectation value, as we know that it will be 0 in for the particle in a box. So even if we have changed the symmetric potential, the physics, you can say that's in the expectation value. In the other case also, it was in the middle only. It was L by 2, if you remember, when we have the simple particle in a box, but now we have a symmetric one and the middle is at the 0, so we are having the that expectation value. And the expectation value of momentum was also 0 in our particle in a box case, and right now also it is 10 to the power minus 16 something. So even though we have the this symmetric potential, the mathematics changed a little bit, but the physics is still the same. From this result you can see. Alright, now we are going to plot the time dependent probability distribution function. So we are going to take a wave function which is a linear combination of mth and nth eigenstate of a particle in a box. So from this two we get the inputs from the user for the mth and for m and n eigenstate number. Then this is the coefficient. Okay, so enter the value of cm square, and t is we have to enter the value of time, and then we know cn will be just equals to 1 minus cm. Okay, and then we will do cm is equal to mp dot square root. So this is the same as has been done in the lectures as well. And then we will get our wave function using our this, and the probability distribution function, as we have seen the equation for the superposition of two eigenstate. We have solved this equation, and I have also shown you this equation in the start of the lecture. So this is just that equation is written here. Probability density for if you have superposition of 2, so you can just check out in the recording in the start or from the previous session as well. And then we are just plotting the same things. All right, and alright, so here let me just take 1 and 2 only. So we have use that example of 1 and 2, so you can check the results from this thing. And let's say we are talking about t equals to 0. Okay, I guess I made some mistake or something. Yeah, so what I have done, I have just the same square. So this is just for the if the first eigenstate is m. Okay, this is for the m eigenstate. Let me just say this is m, and let me just say this is m. Alright, so my first eigenstate I have taken to be 0, so that's why this is just the probability distribution is coming just like the for the eigenstate 2 when n equals to 2. So that's why it is coming like this. Okay, let me just plot it again. Okay. 1, let me take value of 2. Okay, let me take value 0.5, and let me take value like 0. Alright, so here we can see that, okay, it is like this. And then so it is you can check that it is similar to what we have seen in the case of the particle in a box as well. And the time will just be so and we can put different values of the time as well. Sorry, so let me just check if what will happen if I use this. Let's go with 0.5 case, and time is pi by 3. So if time is pi by 3, then we are getting this thing. Okay, so in this case there is a rate change that is happening, is that since we have function from minus a by 2, so this t will be different from what we have observed. So I guess it will be 2 times of this I have to put. So let me just take 2 pi by 3. Okay, there is an error, I guess. Okay, so it can't take this value. Okay, I have to give some 2 times. Okay, I have to give say it is 0.5, and let me just put this value, and okay, let me just cancel this. Right, actually I want the time to be t equals to 2 pi by 3, so let me just multiply it by 2 here, because I don't know what is 2 pi by 3 will be. 1, 2, 0.5. So okay, yeah, so you can see at t equals to 2 pi by 3 now your value has changed. Okay, I put this and I just changed. I don't remember how to just exactly multiply. I have to calculate and put the value of time. So instead I in the code itself I have done a multiply by 2. So whatever I put pi by 3, so it just multiplied by 2. Alright, so at t equals to 2 pi by 3, we will say, so you can play, so this code will be shared, so you can play with it and try to see how this time this t is if you check, this will be a little different as compared to what we had in the case of there's in the case of infinite square well without the from when we have the infinite square from 0 to a. So this time of this thing will change, and that you can see from the equation itself. Alright, so that could be checked. And alright, I'm not sure right now. I guess let's just go to I guess this we are doing in week 1. This is a week 1 stuff, so okay, and let me check if this recording is working. Okay, 30 minutes. Yeah, so basically you can see that. Okay, so what was happening is yeah, it was happening at t equals to pi by 3 only. Sorry, I was a little confused. I thought there was some difference in it, but as you can see, yeah, so yeah, it is happening it was happening at t equals to pi. So as you can see here, so for week 2, this is what we had. Okay, so for 0. So I'm just comparing it for 0.5 right now. So here you can see that let me just go back to the code. Alright, and let's just run it again. Alright, we have eigenstate 1, we have eigenstate 2, let's say 0.51, and let's say go to time 0. So here you can see that, okay, we are having this on the left side, okay, of the box a by 2, and from week 2 also you can see that it was on the right side, but that doesn't matter, it will be on the left or the right, but you can see that, okay, it is similar to that thing. Okay, so this is similar to the previous case. Alright, and what was happening is that it was if you see here, you can see that it was going from t equals to pi by 3, and after t equals to 2 pi by 3 it was coming back because of those this cos 3 omega t1. It was oscillating like this. Now what is happening in this case is that now we are having this psi 1 psi 2, these are actually sine and cos functions, so that is leading to some change. Because of it, you can see that at t equals to pi by 3, which is this time, so if I have 1 and we have 2, and let me just keep it, let me stop this, stop this, let's have 1, let's have 2, let's have 0.5, let's have this t equals to pi by 3, let's have in here. So you can see that t equals to pi by 3 is actually a little different. Okay, so this is changing. So that time. So at t equals to pi by 3, it is not going on the right side, but at t equals to 2 pi by 3, it is happening. So that has changed. So this you can check here. Okay, so this could be checked from the equation, because now we have two different kinds of wave functions. So that's why so in this minus a by 2, this is the difference that we have, that we can observe, that the time has again I'm going to talk about this. So I'm going to show you. Okay, it has gone from left to right, from right to left it has gone. And if I do t equals to 4 pi by 3, alright, so now it is back here. Alright, so the time period that has changed to 4 pi by 3, while earlier it was after 2 pi by 3 only the this probability density that comes back to its position. Alright, so this you can check out why this is the difference by writing this wave function, and if you have any doubt then we check, and you can play with this thing. So here is basically I'm showing you that there is a little difference compared to what we had in our particle in a box case from 0 to a, 0 to a or 0 to a. Alright, so let's go to another. Okay, now we have to plot the position expectation value as a function of time. Okay, so what we are doing is we are again position expectation value as a function of time. So we are again taking the eigenstate m and n. Alright, and then we are putting the value of Cn, and then what we are doing is we are finding the expectation value of x, and this is the probability density function. We know it's going to be like this. Alright, and then we will have this value, which is so this is the expectation value, which is x times probability density times x, and thus we will get the, so this function gives us the expectation value of x as a function of time, because the probability density function has changed, so that's why I have written this function differently. And then we will have this t max is equals to 4 pi by 3. Okay, so maximum value I am going to 4 pi by 3 now, because we have seen that at 4 pi by 3 that is coming back. Okay, and and then but we have this expectation value of this value and the expectation value of this t max times 1 divided by exp txf. So that just find the expectation value at that particular time. Okay, so we from 0 to 2 pi by 3 4 pi by 3 it will find all the expectation value of x, and then we are plotting it with respect to t. So let's just go with 1 and 2 only, and let's just go with 0.5. Alright, so this is the kind of function that we are getting, okay, for 0.5. And if you see it is similar to what you get earlier. Okay, so for 0.5 and this 0.5, the expectation delta, and delta x will be this yeah, so this is similar, so this will be similar. So you can check out for like different values. So 1, 2, 2, 0.99. So displacement about mean, which is the maximum of the expectation value x minus this delta x. So this delta x has now decreased. Here we can see that delta x was low for this values, otherwise delta x was high, right? And okay, So this is the same. So you can see the physics here is still the same, although the time period that has been changed to 4 pi by 3 now. That earlier we were taking time period from 2 pi by 3. So that you can just look into the equation. Okay. So this is the last part of this. Okay. So now we are done with this. Okay. So this code will be shared. So you can just play it along and just try to see. You just stop sharing. Alright, and then you can just try and see how the things are different from our normal, from our periodic this infinite square, where we have taken from it from 0 to a instead of taking from minus a by 2 to a by 2. Alright, let me just go and share the screen now. We'll just do some theoretical problems. Again, we are quite late actually. It's already 14 minutes. Okay. So now we will go to some problem from the Sommerfeld model. So first we will do this problem 1 from the okay, yeah, let's see this. Okay, yeah. First we will do this. Okay. So first we will do this problem 1 from chapter 2 of Ashcroft and Marmol. So here what we have to do is, so we have done these calculations for 3-dimensional case, and now we are going to do the same calculations in the 2-dimensional case, basically in this problem. So it is for the free independent electron gas in 2 dimensions. So the first part is, what is the relation between n and kf in 2 dimensions? Okay, so let's do part A. So for this we will just go similar to what we did for our 3D. Let us consider a 2D square box. Okay, now you consider square box of area A equals to L square. So this could be a 2D crystal in 2 dimensions. So we are talking about some 2D crystal. So what we have is, we have this we are considering a 2D box. So if you remember, in 3D we consider a 3-dimensional box, but now we are just considering this 2D box. Right now, from the time independent Schrodinger equation TISC, which is we have minus h square by 2m del square psi of r vector equals to epsilon times psi of r vector. Now for here for the 2-dimensional case, del square will be equals to, I can take I am taking x and y here, so del square by del x square plus del square del y square. Alright, then again we will use the same separation of variables. Alright, so I can write psi of r vector now, which is a function of x and y, x some capital X of x and capital Y of y. Alright, so we have minus hy square by 2m. Right, I am doing this, and here it is t square x by, now because of this, if I put this equations here, so we will get these two equations, dx square by, okay, let me just show you how we get these equations. So basically what you do, we have minus hy square by 2m del square by del x square plus del square by del y square. Okay, that we have del square times psi of r. Psi of r is now x of x times y of y. Okay, there are two different functions. That will be equal to some epsilon times x of x and y of y. So what will we can write this as minus hy square by 2m. Now this y of x, this del square by del x square, it will just act on this capital X function, not on the y function. So y function will just come out, and we have del square capital X by del x square plus, now you can write del or you can write d square by dx square, is same in this case. Okay, and and then we have minus y square by 2m, and this del square by del y square, then again this will not act on this capital X, and we have del square capital Y by del x square, del y square. Alright, now this gives us some epsilon x of x times y of y, or let me just write it by x and y. Now we will just divide it by x and y on both sides. So what we will have? We have minus h phi square by 2m, 1 by x, d square x by dx square. Okay, let me just take minus h phi square by 2m common, and then we have 1 by y. Okay, so divide by xy on both sides. Just write it. Divide by xy on both sides. So we have, I will take minus h phi square by 2m common, 1 by x, del square x by del x square, and plus 1 by y, del square y by del y square equals to negligible epsilon. Okay, I guess okay, so this is clear. You just divide it by xy, y will cancel out, and you will have just x here, x and y here. Okay, so now this part. Okay, so now what we have this thing which just only depends on, so we on this left side we have only depends on x, and this only depends on y, and this is a constant, and this thing is some constant. Okay, it doesn't depend on x and y. So this thing is a constant, and we have these two values which just depend on some variable x and some variable y, and what we have seen as the summation of this is giving this. This means that each of them must be some constant value. So this implies that this thing must be equals to some constant, which we call as epsilon of x times minus h phi square by 2m. So you can just take this minus h phi square, or what you can do is you can just take this minus 2me by h phi square there to make things simple. But I guess it is understood that this is a constant here as well, and that will included will be called this x, and this will also give you some constant value which we call epsilon y. So now what we have is we have minus h phi square by 2m, 1 by x, del square x by del x square is equals to some epsilon x, and similarly we have minus h phi square by 2m, 1 by y, del square y by del y square equals to some epsilon y. So now we have equation minus h phi square by 2m, del square x by del x square equals to x epsilon of x times x. Alright, and we have similarly we have similarly we have minus h phi square by 2m, del square capital Y by del y square equals to some epsilon y. Okay, now what we can do is we can just go do the same thing as we have done earlier, and we can just write it as minus kx square by x, where kx will be equals to under root of 2m epsilon of x by h phi square. And similarly I can write del square y by del x square. I will just take this minus h phi square by 2m on that other side, and this side is minus ky square times capital Y, where ky will be equals to under root of 2m epsilon of y by h phi square. So you can check this. Okay, this has been done earlier as well, and here also we have epsilon is equals to epsilon of x plus epsilon of y. Alright, so what we can write it, we can write x of x as some a of x normalization parameter times e to the power iota k x of x, and similarly I can write y, which is a function of y only, will be some normalization by ay e to the power iota ky of y. So we will use a trial solution here. Okay, so this is our trial solution, and one can check that this trial solution works. Okay, so I guess we have already done, so I will not do it. So you can just check this trial solution works here, or you can just do it quickly. So we can check that. Okay, we can check this here. If we do this del square x by del x square, this gives us this equation will give us kx, times minus kx square times or iota kx o square times e to the power iota kx of x, right? So this gives us minus kx square iota square and ax times ax square x, that will just have a x of x. So trial function is correct. Okay, so it satisfies our differential equation. Alright, and then let us keep again. Now we will do the normalization part. So so although like you can directly go to, like, the normalization is not needed for this problem, like as you know, but I'm just doing this derivation which has been done for 3 dimension. I'm just doing this derivation just once, so that you can just you will not have any doubt regarding this. So we know that we have to do the normalization for this, and our integration will be from 0 to L. Alright, and generally when you write this is basically 0 to L, so this would be written as x star x times, because it is basically this, where x star is the complex conjugate of this x function, that has to be equals to 1. So what we will have? We will have ax square integration from 0 to L e to the minus iota kx of x into the iota kx of x, and I am considering that this will be mod of ax square, but we can consider it to be real as well, because we just want our wave function to be so this integration, so both of them will give just 1, and this will be just integration from 0 to L dx, that should be equals to 1, which gives us ax square times L equals to 1, and thus we have ax equals to 1 by under root of L. Alright, and similarly we can find ay equals to 1 by under root of L. So this you can do it yourself and check. This is the same, because the equations are basically the same, just such variables are different, x and y, so we will have the same this. So now we have find out psi x comma y will be 1 by L to the power 2 by 3 e to the power iota kx of x and e to the power iota ky of y, or I can write it as 1 by L to the power 2 by 3 e to the power iota k vector dot r vector, where k vector is equals to kx x cap plus ky y cap, and r vector is equals to x times x cap and y cap. Alright, and our energy value epsilon of k vector, that is equals to epsilon of x plus epsilon y, that will be just hy square kx square by 2m plus hy square ky square by 2m, and will be equals to hy square k square by 2. Alright, we need to find a ratio between n and kf. So okay, the problem was just about n and kf, so now we will go I have found a wave function normalization as well, just to do it once completely. Alright, now we will do the same thing, and we will do the same thing as we have done for the 3-dimensional case. Now for the periodic boundary condition, we will have psi of x plus L comma y equals to psi of x comma y. So that will be 1 by L to the power 2 by 3 e to the power iota kx times x plus L, and it should be e to the power iota ky, that should be equal to 1 by L to the power 2 by 3 e to the power iota kxx e to the power iota ky. So we have after cancelling out everything, we have e to the power iota kx times x equals to 1. That, and this will happen if kx of L is equals to 2 pi n of x. For this you should use this, e to the power iota x is equals to e to the power iota theta is equals to cos theta plus iota sin theta, right? So just use this, and you know that for this to be 1, sin theta has to be 0, sin theta is 0 for and cos theta has to be 1. So cos kx has to be 1, so that means kx equals ks times l has to be equal to 2 pi times n of some integer n of x. So integer n of x. So from here we have derived kx is equals to 2 pi nx by n. Alright, and similarly you can find ky is equals to 2 pi ny divided by l. Right, then we will go into the we're going to do another thing. Now area occupied by a point in T space that I define by delta k, that will be equals to, since each of them you can as the same description as we have seen in the lecture for the 3D case, same goes with the 2D, and it was shown in the 2D form only. So it will be 2 pi by l times 2 pi by l. Okay, it will be a square of 2 pi by l to 2 pi by l whole square. So that gives us 4 pi square by l square. Alright, then the number of around value of K space inside an area capital A will be capital A divided by delta K. Alright, now okay, so this will be capital K times delta K. Okay, and now this area, the area A in K space is the area of a circle with radius kf. Alright, so as we have done for the 3-dimensional case as well, so 3-dimensional it was a sphere, in 2D this will be a circle, so we have kf. So area A will be equals to pi k square, where kf will be the radius. Okay. Similar to 3D case, in 2D there will be a circle and kf will be our radius, so it will be pi kf square. So in 3D we were taking volume, in 2D we will take area in the case. Now taking into account the number of spins number of spins for the electron, we can write n equals to n, which is basically capital N divided by this total volume L square, total area L. Okay, this area L square, which is basically in real space. There is a total area in real space, which is number of electrons per unit area. Now this will be just one minute. This is the number of electrons per unit area. Alright, so now this so what will be this? Then this is total number of electrons per unit area. So this we know that there is a number of around values of k space inside an area A will be, and each k point will have number of around value of k space. So that is the space of one k point, and each k point will have 2 electrons. So as we have done for this, so for 2 times this area, which is A divided by delta k times divided by 1 by L square. Alright, so now this will be just 2 times pi of A square divided by delta k, and delta k was 4 pi square by L square. So L square will go up and L square we have down. So we have L square will L square will just cancel out each other, and there will be a cancellation of this pi, and there will be a cancellation of this 2 here. Yeah, so what we will have n is equals to what we are left with? We are left with kf square upon 2 pi square, 2 pi. So this is the relation that we want. Okay, so that is the relation between n and kf that was asked. So n is equals to kf square upon 2 pi, or from the same, what I can write is kf I can write as 2 pi n to the power 1 by 2. Okay, and remember in 3D case, what we had is we had kf is equals to 3 pi square n to the power 1 by 3. So that is the difference from 3D and 2D. Alright, let's go to the part B. Now in part B, what has been asked? Okay, in part B it is asked that what is the relation between kf and rs in 2 dimension. Okay, so we need to find the kf and rs in 2 dimension. So what is rs? Yeah, so rs, as we know, rs basically is defined as the radius that will give us the area or the volume, like in 3D with the volume that an electron occupy. Okay, so that will be equals to 1 by n, 1 by n in case of volume, or 1 by n, here our n is the area. So now what we have 1 by n is equals to this pi times rs square, where this is basically this is the area occupied by 1 electron. Okay. Right, so let's just go. Okay. So this is the 1 by n equals to pi rs square, which is the area occupied this, and we just want the relation between rs and kf. So what we have to do, we know rs, relation between rs and n. We can define it. This is the area pi rs square, and I can write this rs equals to 1 by n pi divided by to the power 1 by 2, and then n we have already found that the relation between n and kf is this. So I can write n as kf square upon 2 pi. So it will be kf square upon 2 pi will be here, and I will have a pi here to the power 1 by 2. So after cancellation, rs we can see that it is root 2 upon kf. This is our part B. Let's do part C. So what is given in part C? Okay, prove that in 2 dimensions the free electron density of level which is g epsilon is a constant independent of epsilon for epsilon greater than 0 and 0 for epsilon less than 0. What is that constant is? So we basically have to find the density of states for in the 2-dimensional case. So in the lecture you have found the density of states at the end by dn by de formula as well. So that could also be done, but I will do this derivation for two dimension, and in the next program for the one dimensional case in the similar way as it was done as you had done for the two dimensional. Basically, we can find our electron number of electrons from by an integral over the k space, and then we change that integral from k to this epsilon in the energy integral, and then the function which is along with the Fermi-Dirac distribution function, that part of the energy function, that is going to be our density of states. So it will be similar to what has been done for the three-dimensional case. So I will do this derivation for two dimension, and in the next one for the one dimensional case in the similar fashion. Alright, so let's just do it. So in 2D, so I'm talking about the last part of this week's lecture. So in the last session, this is the programming session, it was shown that how you can calculate dots using two-dimension dot. You have the result there, and it is by you can find dn by de form as well, but I am using the dots from by going from the k space integral to energy space integral for the number of electrons. Alright, so yeah, as has been done for the three-dimensional case. Okay, so let's do it. In 2D, the number of electrons per unit area can be calculated as n is equals to 2 times from minus infinity to infinity dk vector upon 4 pi square. Now here in case of 3D it was 8 pi cube. In case of 2D this will come as 4 pi square times f of epsilon of k vector. Right? Yeah. Now where this epsilon of k vector that we have, that is our Fermi function. Right? Okay, now here now how we can write for two dimension, how we can write this dk vector. Now this dk vector could be written as in three dimension it will be written as 4 pi k square dk, which is the area of the shell. In this case we have a circle already, so dk vector will be equals to this parameter only. Okay, so we have this, so this dk will be equals to dk time 2 pi k dk. Okay, so that will be of a disk. Basically, instead of a sphere, now we will have a disk. The area of a disk is 2 pi k dk. Alright, so this thing, this is our k. Let's do this. My square is not. Alright, this is your dk. Okay, and this area, that will be our dk vector. Okay, this is the dk length, and this will be like k radius, so this area will be 2 pi k times dk. That will be our dk vector divided by 4 pi square times whatever our f epsilon is, right? And then we can just do the cancellations and all. Okay, so this is 4 pi and all, so whatever we have is k dk divided by pi will be here, yes, pi times and in the multiplication of 2, we know that is for the spin. I didn't mention it, but you already know, you must already know that is for the spins. Now again we will go from k to k integral to energy integral. Now we know energy is given by h phi square k square by 2m. Alright, so from here I can write k is equals to 2m epsilon upon h phi square 2m epsilon upon h phi square whole to the power 1 by 2. Right? That will be k. right? And then we can write d epsilon from here as h phi square k dk divided by m. So from here I can write k dk. I will take k dk because I know I have here k dk, so I will just take k dk will be equals to m upon h cross times d epsilon. Alright, now using this we will just put it in n. Now k dk, I have a 1 upon pi, and just take it out. Now instead of k dk I will write m upon h cross times d epsilon, right? And in case we don't have any k left in the integral, so now we just have the f epsilon. So here you can see that and now for energy value, this integration will go from 0 to epsilon. Alright, now this n, so here we can see that our integration has changed. This n has become n equals 0 to infinity from m upon pi h cross f of epsilon d epsilon, and this will be our density of states in the 2D case. Alright, so we have find G2D of E, two-dimensional laws in 2D case. That will be equals to m upon pi h phi square for epsilon greater than 0, and this will be equals to 0 for epsilon less than 0. Right? This is our answer. This is what we have to prove. And like this is it's constant. The density of state is constant, and this is the constant value m upon pi h bar square. Alright, let's quickly go to part D now. This was part C. Now in part D, what you have to do is show that because G epsilon is constant, every term in the Sommerfeld expansion for n vanishes except the t equals to 0 term. Reduce that mu equals to epsilon f at any temperature. Okay, so let's do this part D. So here again we know the Sommerfeld expansion. We have minus infinity to infinity h of epsilon f of epsilon d epsilon equals to minus infinity to epsilon of f h of epsilon d epsilon plus mu minus epsilon of f h of epsilon plus pi square by 6 1 by beta whole square h prime of epsilon. Alright, so this is our Sommerfeld expansion. Now for n, this h of epsilon for n, which is our free electron density. So we are letting this kind of integral for our electron density. This will become G epsilon. Okay, so and here we have G of 2D, which we know is m upon pi h phi square for epsilon greater than 0. Right, and it is equals to 0 for epsilon less than 0. Alright. Now, so what I can write this n is equals to from minus infinity to infinity G of 2D of epsilon times f of epsilon d epsilon. Then we will use this Sommerfeld expansion. So we will have, I can write it as minus infinity to epsilon f. I can just write this integral from 0 to this because it is 0 for less than this, energy less than 0, plus we will have mu minus epsilon of f G of 2D of epsilon of f plus pi square by 6 1 by beta whole square G of 2D prime epsilon of f. Alright, and okay, time of study of this. Now again, now we know that again we can see from our in this case it is asking that this will become 0 for all other cases, and then we know that we do this thing at constant volume. So it will be for n equals to n naught, sorry, these are done at constant pressure. Right, so in the problem it is asked that z is constant, every term in the Sommerfeld expansion for n vanishes except the t equals to 0 term, and reduce that mu is equals to epsilon f at any temperature. So since we as we know that we find all the thermodynamic properties are calculated at constant volume, then we know that we can do this n equals to n naught. So, and this is our n naught. Alright, so so basically that is how we determine our chemical potential. So as we have done earlier as well. So to determine, so what I will do, I will determine mu. To determine mu, what we need is okay, now to determine mu, we can say that okay, all the thermodynamic properties are measured at okay, so as we know, okay, we study thermodynamic properties. So instead of doing it a constant volume, let us continue it. So this is our n naught, and what it is in this question, what it is asking is that, so we will not do it in the same in that fashion, like we are saying it constant volume. It is saying that since it is the g is constant that we have proved, every term in the Sommerfeld expansion for n vanishes except for t equals 0 term. So every term will vanish except for j equals to 0 term only. So so I will just we will just solve this expansion term. So, and we will see that all the other terms, all other terms will vanish except this and 0 term. Alright. Now first, so what we can do? So now what we can do? We can just put our this g of 2d of epsilon. So what we have is, we have m upon pi h phi square, which is a constant, times d epsilon, plus I have nu minus epsilon f. I will have m times m upon pi of h phi square. Alright. I have this nu minus epsilon of f, plus now this prime, this will be 0 because the derivative, because g of 2d is constant, so this derivative is 0. So we have just these two terms. Okay, so yeah, I'm just basically not using that n equals to n naught thing here that was done in the lecture. So we are just going with the Sommerfeld expansion. We are just doing the calculation. We are just in this we have to show that within the Sommerfeld expansion all the terms will be 0 other than this n equals to n naught, this n naught term will be other than this n naught term. Now what we have m upon pi h phi square, d epsilon, this is just give us this, and now we have nu minus epsilon of f times m upon pi h phi square. So what you will get is we get m times nu pi h phi square. Alright, so this is what we are getting, our n value is. Now here we know our n is equals to kf square upon 2 pi. Okay, so so our n is coming as m times nu divided by pi h phi square. Now we have kf square upon 2, so we have 1 upon 2 pi times, now kf could be written as if we know epsilon of f is equals to h phi square. Let me just write it in green. We have epsilon of f is equals to h phi square kf square by 2m. Alright, so I can write my kf from here. I can write my kf as from this, using this I can write my kf as 2m epsilon of f by h phi square whole square. Alright, so we have kf square, so kf square could be written 2m epsilon f by h phi square from this equation in green. So I get n is equals to, cancelling out, I have m epsilon f by pi h phi square, right? So we have m epsilon f upon pi h phi square. Now this was our equation 1 that we get from Sommerfeld. Okay, we just use the Sommerfeld equation, we got into n, and we use our definition of g2d. The third term is automatically 0, and on calculating we get n equals to m nu upon pi h phi square. And then we know that our n, we know n relation between n and kf from part A. We use that relation, and then we found that n is equals to this m epsilon f. Okay, so this is our equation 1, and this is our equation 2. Now using 1 and 2, what we can see is that nu is equals to epsilon f. Alright, you can just check. Okay, this m nu upon pi square is m epsilon f pi square, both the values are same, then mu should be equals to epsilon of f. So we can see that this term nu minus epsilon of f, the second term which was this mu minus epsilon of f times g2d of epsilon of f, mu minus epsilon of f times g2d of epsilon of f. Okay, this is h of epsilon of f. Okay, 1 minute. This is h of epsilon of f, and this is also h of epsilon of f. H is 70 epsilon integration minus h of epsilon of f, h prime of epsilon of f. Yeah, sorry about that. Okay, this is the Sommerfeld expansion. Okay, I hope I have written the Sommerfeld expansion correctly. Let me just check it. Okay, yeah, got it. G of epsilon f. Yeah, I just got confused a little bit here. Sorry about that. Okay, yeah. So it is h of epsilon of f, and we have the g of 2d of epsilon of f here. Okay. So the second term, this is which was nu minus epsilon of f times g of epsilon of f. G 2d of epsilon of f is also 0 along with the third term, in the Sommerfeld expansion. Sommerfeld expansion. So we have to show that every term in the Sommerfeld expansion for n vanishes except the t equals to 0 term in the Sommerfeld expansion for n. And only surviving term is for t equals to 0 Kelvin, which is n naught. This n naught. Alright, this is our n naught. Alright, so this we have for only this n naught term will survive. Alright, this n naught term will survive, and we have also deduced that mu will be equals to epsilon f. This is also we have deduced. Alright, so this is part D. Okay, those two things were only there. Alright, and now we have part E. So now we have to deduce from 2.67 that when g of epsilon is S and C, then nu plus kBT is given by epsilon of f. Alright, so what we have is, okay, now what we are going to see, we are going to check this analytically, basically. So analytically it is showing that if we do the actual calculation for our n, so we are here in part D, what we did is we use the Sommerfeld expansion to calculate the electron density. In part E, it is asking us to actually do the integration and see that you will find nu to be like this. Okay, it will be something like this. So let's just see. It will not be epsilon f, but it will be something like this. So let's just check it. Now from equation 2.67, which it is talking about, so that you can check from the book. Check from the book. This n, basically it is saying that minus infinity to infinity. This is the equation, g epsilon f epsilon d epsilon. Alright, now in 2D we have g epsilon is equals to m upon pi h phi square. Okay, and we have f epsilon, that is equals to 1 upon 1 plus e to the power beta epsilon minus mu. Alright, so this we have. So we will just put it here. We have integration now 0 from infinity, because g is the energy value we are defined they are from 0 to infinity. Now g of density of state m upon pi h phi square, and then we have the Fermi function, which is 1 plus e to the power beta epsilon minus mu. Alright, now so we can just take out this constant h phi square here. We have 0 to infinity d epsilon times, we have to do this integral 1 plus e to the power beta epsilon minus mu. Now let beta times epsilon minus mu is equal to some constant t. To solve this integral, we will use that this is equal to t. So what we have, beta times t epsilon will be equals to dt, right? And so our n will be equals to n times pi h phi square, integration from at epsilon 0, it will be now minus nu beta, and at epsilon infinity it is dt, right? And d epsilon will be is equals to dt by beta, and we have 1 upon 1 plus e to the power beta e to the power t. Alright, so this is our this is the integration that we have to find. So I can take this beta outside, so let me just take this beta outside. So 1 by beta here. So this stuff to the side, beta side here. Alright. So we have m equals to m pi h phi square. So I will have n equals to m upon pi of h phi square times 1 by beta times, we have integration minus nu beta to infinity dt upon 1 upon, or I will just write it as dt upon 1 plus e to the power t. Alright, now we have to find this integral. Let's say this integral is I. So let me just calculate this integral I. So now I will be equals to, let me just do it in this green here. So now I will be equals to, I will have, and let's say this, and let this minus nu beta is equal to some t naught. So we have integration from the t naught to infinity dt upon 1 plus e to the power t. Now to solve this integral, what we can do is we can write here on the in the numerator we have a 1, so I can write 1 plus e to the power t plus e to the power minus t. Okay, that is just 1. E to the power t plus e to the power minus t will be 0. Here 1 plus e to the power t dt. Alright, so we have this. So now we have so we are solving this integral I. Now this will be equals to again t naught to infinity. So we can break this integral now in two parts. One will be this 1 plus 1 will be this 1 plus 1 plus e to the power t 1 plus e to the power t dt plus another will be t naught to infinity e to the power minus t upon 1 plus e to the power minus t dt. So this will be just 1. Okay, this will be, if you just write, this will be just 1. So So this will be just some just so I will just be equals to this some t from t naught to infinity. Okay, and then we have this now we have to do this integration from t naught to infinity e to the power minus t upon 1 plus e to the power t dt. Now what we can do to do this integral, let we take 1 plus e to the power t as some u. So we have e to the power t dt, alright, that will be equal to some du. Alright, so now our integral I will be equals to t from t naught to infinity, and this will be some okay I guess I mean okay, this is this sorry about that. Okay, yeah, so we can write 1 plus e to the power t minus e to the power t divided by 1 plus e to the power t, so this will be 1, and yeah, this is e to the power t, and there will be a minus sign here. Okay, sorry about this. Okay, and there will be this. Okay, now it is here. Okay, so what I have written this dt by 1 plus e to the power t is t naught to infinity, and 1 I can write as 1 plus e to the power t minus e to the power minus e to the power t. So e to the power t minus e to the power t, that will be 0 and it will be 1. Right, I put the minus on the wrong side. On the wrong, actually I put it on the exponential, but it is here. Alright, now it is clear, I guess. 1 plus e to the power t 1 plus e to the power t dt minus integration t naught to infinity this, and minus integration t naught to infinity power t 1 plus e to the power t dt t naught to this, and to do this integral we can take 1 plus e to the power t as u, e to the power t dt will be equals to du. So what we have, okay, is for t naught, this will be u will be we have integration u, so u equals 1 plus e to the power t naught to infinity again, and we have this e to the power t dt will be du divided by 1 plus e to the power dt, which will be u. Alright, now it is completely clear. Okay, alright, okay, so this is our integral, and what we will have, I will have I is equals to t from t naught to infinity minus I have ln of u from 1 plus e to the power t naught to infinity. Now ln of x, ln of u of infinity will also be infinity, so you can see that both these infinities will just cancel out, so the infinite, so we are left with just some finite terms here. So you can take infinity, you can take a very high value, and you can understand that both the high values will mostly cancel out each other, because ln of some infinite or very high value is also something infinite only. So what we left with is minus t naught plus ln of 1 plus e to the power t naught. Now we will use what was our t naught. We had said that t naught is minus mu beta, so I can write my I as minus mu beta plus ln of 1 plus e to the power minus mu beta. Right? So it is t naught is minus mu beta, so it will be mu beta, because we have minus mu beta plus ln of 1 plus e to the power minus mu beta. So from here we come back to our n. Our n is equal to m upon pi h phi square times 1 by beta times I, and I we have found will be equals to mu beta plus ln of 1 plus e to the power minus mu beta. Right? Now since beta is equals to 1 upon, okay, here now here remember that beta is equals to 1 upon kbt, so I will just open this bracket, and beta will just cancel out. Just keep the m upon pi h phi square common here. I will take beta inside, so we have mu plus 1 by beta will be just kbt ln of 1 plus e to the power minus mu by kbt. Alright, and now for 2D case, we know our n is equals to m epsilon f upon pi h phi square. Okay, this we calculated in our previous part, if you remember. Okay, so in previous part we have found that n is equals to m epsilon f upon pi h phi square. So we are using that result in this part E now, what we find in part D. So what I will do, I will put this m epsilon f upon pi h phi square here, right? We will have m upon pi h phi square times we will have mu plus kbt ln of 1 plus e to the power minus mu upon kbt. Alright, so what we will have epsilon of f is given by mu plus kbt ln of 1 plus e to the power minus mu upon kbt. And this you can check, this is what the question has asked, so you can go and alright, so this we can check, and this is what the question is: mu plus kbt ln of 1 plus e to the power minus mu by kbt in part E. This is what has been asked. Alright, and now let's just go to now we have to do our part F. So here we can see that from Sommerfeld model we get mu is equal to epsilon f, but now there is a difference. Nu minus f is not equal to 0 if we do the exact calculation. So that is now what is the in part F is. Now comparing the results of part B and D, the Sommerfeld explanation works for 2D free electrons or not. Okay, so I have changed. So in the book the F part is a little different. So so I'm not because that has not been discussed in the lecture. So if you see in the book, this F part is little different. So I have included this F part on my own. So now we in F part we are just asking this is the company that is a part in D. The Sommerfeld explanation works for 2D free electrons, and we can see that it doesn't work. And in the lecture note as well, you have checked it using the Python code, and here we have analytically solved it and shown and we have seen that yes, it that doesn't work. So model doesn't work for this. So we can just write comparing results from part D and E. We can see that Sommerfeld expansion for n, I should have written it for n actually, for n does not work for 2D free electrons, right? So it doesn't work for 2D free, and it will not work for other as well. You can check. Okay, so basically for 2D free electrons, this Sommerfeld expansion doesn't work, and we have checked it for the free electron density. Alright, so let's go to problem number 2 now. We're already quite behind. We have quite less time. Okay, so let's just do some small problems for one-dimensional case. Okay, this we can do quickly. So now for the one-dimensional case, again we are asking the same. It is asking the same things. We have to find the relation between n and kf now. In case of 1D, now for 1D, let us consider 1D line of length L. Now you can take the example for this, like you say, okay, 1D might be something completely theoretical, but in 1D we can consider, like, an example 1D could be a one-dimensional quantum wire in which there is free electron gas. Okay, so we can consider it in 1D. In physically we can consider it as a one-dimensional quantum wire where there is a free electron gas, right? So if you have to define it in a kind of a problem, so we can consider it some quantum wire, Alright, then let's take from 0 to, okay, so this is kind of the problem that we have from 0 to L. Now earlier we have 3D, we have a box, in 2D we have a square, and now 1D you just have a line. Now doing the time independent Schrodinger equation, same time independent minus h square by 2 and del square psi by del x square. Now here the del square will just be in one dimension only, so we have just del square psi by del x square. Again we will have the same del square by del x square, which is a function of x only. That will be equals to minus k square times epsilon times psi of x, where times psi, it is psi of x, what I am just writing psi. Avoid confusion. Now where k is equals to again our 2m epsilon upon h phi square, right? So again what we can consider psi of x as e to the power iota kx. Okay, then if we do the normalization again, so this is the same as we have done earlier. Again we have to do 0 to L a squared a squared times dx equals to 1, and we get a equals to 1 by root of L. So I am just skipping it because we are already done it. Again it was not required for our problem, but just for the sake of completion, for 1D also we will have 1 by root of L. This will be our wave function for the periodic boundary conditions, and energy as k we know h plus by k square by 2m. Now for the periodic boundary condition, it is not work for the periodic boundary. We are now going to apply the periodic boundary condition. Periodic boundary condition. Sorry. Right. So now we have psi of x plus L. That has to be again equals to psi of x. You can again write 1 by e to the power iota k. X plus L has to be equals to e to the power iota kx. So if we have e to the power iota kl has to be equals to 1. That means kl has to be equals to 2n pi, and k will be equals to 2n pi by L. Right? This is we have derived. Now again it's the similar thing that we did in 2D. Now there will be just length instead of area, length occupied in k space. So length occupied, so length occupied in k space by a point in k space, by a point in k space, that will be equals to again given by delta k. Now we are just in one dimension, so this delta k will be equals to 2 pi by L, right? Because it is 2 and pi by L, so it will be 2 pi by L. So we will have k points at separation of 2 pi by L, right? Okay, and then we have the number of around L, the number of around values of k space and length gamma, number of around values of k space and length gamma will be gamma divided by delta k. Now here our the length gamma gamma in k space is line from minus kf to kf. Remember, kf was radius remember kf was radius in 2D and 3D case. Alright, so the length will be the diameter now. Okay, I should have written it in red. Okay, that's fine, I guess. So that's why, so basically so here gamma is basically equals to 2 times of kf. Okay, so it will be kind of a diameter. Okay, just write it in D. Diameter in case of 2D. Okay, so it was the diameter in case of 2D. So in 3D we have taken in 3D and 2D we have taken kf as the radius. So now when we go into 1D, the length that we take that will be the complete diameter, and the diameter will be is 2 kf. So the length that we are considering in this case will be from minus kf to kf, which will be 2k, which will be length 2kf. Alright, and kf is our Fermi vector, so I have not mentioned it anywhere. Now taking into account, again it's the same thing, taking into account number of spins for the electrons, we will write n will be now number of electrons per unit length. Okay, so this will be a number of electrons per unit length, that will be equals to capital N divided by our total length L. Now that will be it will be 2 times n by L, total number of electrons divided by L. That will be equals to 2 times of what we have our 1 by L times 2 times, so there will be 2 times of it will be 1 by L times 2 times, this is for the spin, 2 is we have electrons with 2 spins, so we have 2 time gamma divided by delta k, which gives us the number of around k values in this space, and gamma is 2 kf here. I will just put this value, it is 1 by L, it is 2, gamma is 2 times of kf, and delta k we have found is 2 pi by L, so it will be 2 pi by L, 2 pi times L, and after cancellation what we have n is equals to, okay, after cancellations we have 2 kf upon pi. So this is the relation between n and kf now, or I can write this kf is equals to n pi by 2. Right, so this is the relation in case of 1D. Alright, let's go to part B and part C quickly. So part B is what is the relation between kf and rs in one dimension. Again we are going to ask the same thing, relation between kf and rs in one dimension. So again we have 1 by n, now this is the number of electrons per unit length. Number of electrons per unit length. So 1 by n will be equals to now 2 times of rs, where this gives us, this is the length occupied. Okay, so rs was the radius of the like the sphere and the circle that the electrons occupy in the real space. So now this r is the radius, so now we will talk about in terms of diameter. So the length will be 2 times of rs, length occupied by, length occupied by an electron moving in 1D, in one dimension. So now and we have found n is equals to 2kf upon pi. So 1 by n will be pi divided by 2kf, and 2 times of r will be 2 times of rs. So our r of rs will be just equals to pi by 4kf. Right, rs will be equals to pi by 4kf. Now let's go to part C. Okay, now what is part C? In part C we have to determine the density of states in one dimension. Okay, so that is just the density of, we have to determine the density of states in one dimension. So again we will do the same thing. Now I am just doing it fast because we are already quite out of time. So we can write n is equals to this to this. We can have a dk vector. Okay, so let it will be dk vector divided by 2 pi this time, instead of, okay, if I 8 pi cube 4 pi square, now it will be 2 pi times f of epsilon of k. Alright, and now we can write this as n is equals to 2 times, it will be whatever the range minus infinity. Now this dk, again this dk could be written as earlier it was initially it was the volume, then the area, and now it will be the length, and it will be 2 times of dk, 2 dk divided by 2 pi times whatever we have f of epsilon. Okay, again we will use the same relation, and epsilon equals to h square k square by 2m. So here this implies k is equals to 2m epsilon upon h square to the power 1 by 2, and we will have d epsilon which will be equals to hy square k by m dk, or I can write dk is equals to m upon h square k times d epsilon. Okay. Using this, now what we have n is equals to, and here 2 to cancel, we have I can write it as a 4 times integration of from 0 to infinity. I am still keeping this 1 upon 2 pi that I had here, right? I will just take 2 outside, so I will have 4 times 0 to infinity upon 1 upon 2 pi. Instead of I will have the f epsilon, and then instead of dk I will have m upon h square k. Now k could be written like this, so that will be equals to 2m epsilon h square whole to the power 1 by 2 d epsilon. Alright, so this is what we will have, and if we solve it, taking out all the constant, we have 2m upon h square whole to the power 1 by 2, and we have 2 upon 2 pi. Now one two I have taken here. Okay, one two I have taken from here, so I have 2 upon 2 pi now. Right, 0 to infinity epsilon to the power minus 1 by 2 f of epsilon d epsilon. Alright, so using this, what is our g of 1d of epsilon? Okay, this is the density of C, so density of C will be whatever with f epsilon is. This constant I have taken it out. Okay, let us not take this out. Then it will go to 0 to infinity this. Alright, and here. Alright, so we have this thing, this is the integral, and so this will be our whatever is with this g epsilon, this will be our g of 1d of epsilon. Okay, so this is our density of state in the 1d case, g of 1d of epsilon, that will be equals to 1 upon pi 2 upon h square whole to the power 1 by 2 times epsilon to the power minus 1 by 2, let me just write it as 1 by under root of epsilon. Okay, So this is what we know from the lecture. It is going to be 1 by root of epsilon proportional to that. Alright, so this is our density of 3 in case of one dimension. Alright, so this is our last part for this problem number 2. Let's go to problem number 3 now. Alright, now problem number 3 is a numerical problem. So let's see the time. I guess I don't have enough time now. Yeah, so I guess we can only do now this problem number 3 only, and the next problem we have to do in the coming session. Alright, so for problem number 3, what we are given this pi value 3.14. We are given electron density of the lithium. We are given the mass of the electron, h bar value, 1 car, what is 1 car in joule, r value, and the this electronic charge as well is given, and kV value is also given. And we have to this 3 parts we have. Let's quickly do them. So now for part A, what we have to find, we have to calculate the Fermi vector Kf, Fermi velocity Vf, and the Fermi energy Ef or epsilon F. So so these problems are just putting the value. So you just have to, so Kf will be given by 3 pi square n o to the power 1 by 3, and then you just have to put the value where n is the electron density. Okay, n is the electron density, let me know. Alright, this is from the 3-dimensional case. So just by putting all the values, you just have to put the values. 3 times 3.14 whole square times n will be your 4.7 into 10 to the power 22. Now these are given in centimeter cube, so our answer will also be in centimeter. So just take care of that. So our answer will be centimeter inverse, because 3 and has only the dimension. It has a dimension of per centimeter to the power minus 3. So our answer will be centimeter inverse. So in this problem, mostly you just need to take care of the units. So if you do the calculation, the Kf approximately comes as 1.12 times 10 to the power 8 centimeter inverse. Okay. Then next we have to we have to find now the Fermi velocity and the Fermi energy. But first I will calculate the Fermi energy. So Fermi energy here h5 square kf square by 2m. That is the mass of the electron. Again we just have to put the values of all of them. Okay, so we just have to write 1.05 into 10 to the power minus 34 whole square times kf is given. Now here remember that this h5 square that I am writing, that is in the unit of SI unit, joule second. Now here either I can do this. Okay, so the one thing, either I can do this, or I can actually we know kf in terms of n, so I can just use h5 square by 2m 3 pi square n to the power 2 by 3. So I can just use the electron density, and then just with the electron density I can calculate. I don't need to use kf, but we have already calculated kf, so I will use kf here. So I will use h5 square kf square by 2m this time, and then you just have to put the values here. So it is 1.05 into 10 to the power minus 34. So remember that this is whole square and this is in SI unit. So we have to put our kf also in the SI unit. So our kf will be 1.12 that we calculated into 10 to the power 10 this time. Okay, we have calculated 10 to the power 8 in centimeter inverse. So you have to convert it in meter inverse. So 1 meter equals to 10 to the power 2 centimeter. So 1 meter inverse is equals to or I can write like 1 centimeter. So 10 to the power 2 meter inverse will be equals to 1 centimeter inverse. Okay, here is write it here properly. So you know 1 meter is equals to 10 to the power 2 centimeter. So 1 meter inverse will be equals to 10 to the power minus 2 centimeter inverse. It means 10 to the power 2 meter inverse will be equals to 1 centimeter inverse. Alright, so this is the unit conversion. So kf we had in centimeter inverse, so you have to convert it into meter inverse. So for that, 1 centimeter inverse equals 10 to the power 2 meter inverse. So you have to multiply by 10 to the power 2, which makes 1.12 into 10 to the power 10 whole square. Alright, so you just have to take care of units in this kind of problem. Otherwise, you just need to and just need to remember the formula. And the mass of the electron is also given to you, and this is also in SI unit. 10 to 9.1 into 10 to the power minus 31 to the power minus 31. Alright, so the unit you can check, the unit will become in joule. You can check by cancelling of the units. You can check the units will come, the unit of this will be in joule. So we will have epsilon of f will be, if we calculate, we will get 0.076 into 10 to the power minus 68. So 10 to the power minus 17. Final answer is minus 10 to the power 0.076 10 to the power minus 17 joule. Okay, and note that one electron. So we can leave this answer here, but generally we know that we have this Fermi energy in terms of electron volt. One electron is 1.6 to the minus 19 joule. So I can write my epsilon f. Some of these values are provided in the lecture, so you can match them. So they approximately match because of the approximation that we have taken. We have taken the approximation for pi, and then whatever the approximate value is, then those we are using to calculate the further values. So there will be some difference in the decimal place if you check from the values which are provided in the lecture note for the lithium using the Sommerfeld model. Okay, now and SINF, if you calculate, you use this 1.7 minus 19 joule thing. Okay, so you just divide it by 1.7 minus 19, you will get it as 4.75 electron volt. Alright, and the last part we have to, and then the part we left is the Fermi velocity. Now Fermi velocity I left because we know that the kinetic energy is given by epsilon f in this case for a particle in a box, because there is no potential energy. So that will be equals to, and that will is given by half m vf square. This is how we define the Fermi velocity. So epsilon f times half of m v square vf square is the Fermi energy, right? So I can write vf as 2 epsilon f upon m o to the power 1 by 2, and again basically we can write 2 by m times I can write epsilon f as s y square kf square by 2m o to the power 1 by 2. So either I can use the value of epsilon f that we have that we calculated right now, or we can use the value of kf, or we can go back to electron density. So you can see that if you know, basically if you know electron density, maybe h pi square m square, it will be 3 pi square n o to the power 2 by 3 o to the power 1. Alright, so and I'm not so we are not going to use this equation. I am going to use this one only because we have already calculated epsilon f. So I will use this one, but like this you can see that with electron, only with electron state as well, I could have directly calculated VF already. The only thing is that I have to go from, I have to know the ratio between epsilon f and kf, and then kf and n. Then I can calculate VF directly from the electron density. But here let us calculate it from the Fermi energy. So I will we just again have to put the values in. So here we will just put the values in the SI unit for epsilon f, 0.76 into 10 to the power minus 17 joule that we got, divided by the mass which we have in the SI unit, 9.1 into 10 to the power minus 31 kg, and we will have the power 1 by 2. And if you calculate it, you will get your energy in terms of meter per second, which is 1.29 into 10 to the power 6 meter per second. And to compare it with the lecture notes, we can convert it 1.29 into 10 to the power 8. 1 meter equals to 100 centimeter, so centimeter per second. Alright. Okay, so okay, so we are already out of our 2 hour session. Right, it's already 9:11 as well. Okay, alright. So now we have for part B, you have to calculate. So let me just give you the formulas for part B and C, and I will start in the next session. I will just show you the solution for this. But it is basically, as you have understood, you just have to put the values in the formula, and that's it. All you have to do is take care of the units. So this kind of problem you have in the week 3 assignment as well. So you just have to put the values in the formula, and you can go back as well, like you just need the electron density and you can calculate other stuff. So let me just do it for B as well. So B, we have calculated this CV per mole. CV calculate the heat capacity constant value CV per mole of free electron gas for lithium at T equals to 300 Kelvin in cal per mole per Kelvin. So we know CV per mole of free electron gas. Alright, so this, if you see the lecture notes, so this is given this formula is given, this is pi square by 2 T by TF Z times R, where Z is the valency. So this is the valency. Alright, and TF is our Fermi temperature. Here TF is our Fermi temperature. So we know that TF is given by epsilon F upon KB. Alright, and again we know that epsilon F we can write it from KF in N. So you can calculate KF, TF from using that thing. The similar way, using the writing epsilon F in form of KF and then writing KF in terms of N, you can calculate TF directly from the electron density as well. But I am not going through the similar way as we have done for this VF stuff. Alright, BF and epsilon F and all. From epsilon F go to KF and from KF go to N. But we have the epsilon F value, so we can just calculate directly from there. And if you put all the values, you will get KF TF is equal to 5.51 into 10 to the power 4 Kelvin. Alright, let me just write. Okay, so like basically you can use 1 by KB, you can use it as h5 square kf square by 2m, or then you can go further to h5 square by 2m kb, which will be 3 pi square n to the power 2 by 3. Alright, so you can either use this or you can use this formula, but we are going to use this formula here. And if you use this formula and the epsilon F value that we Fermi energy value that we have calculated, TF comes at 5.51 into 10 to the power 4 Kelvin. Alright, and then we just have to put this in CV per mole. Okay, just put all the values in. This 3.14 whole square divided by 2, and I am putting all the values we are going to put in the SI unit first. Okay, we get 5.51 into 10 to the power 4 D by TF times valency is 1, and we have 8314, and this will come as in joule per mole Kelvin. This you can check, and this you can check. The only one which has the dimension is the R, so we have shown that, and the value will come as 0.2232 joule per mole Kelvin. But the question asks us to find it in Kelvin, in cal per mole Kelvin, and 1 calorie is given to us as 1 calorie is equal to 4.184 joule. So you just have to divide this by 4.184. So you will get the answer 0.053 cal per mole Kelvin. Right. So this is our answer, is CV by mole. Alright, now let's do our last part, which is part C. Okay, part C, we have to calculate thermo power Q, which is also known as the thermoelectric power or the Seebeck coefficient. So what is this Q is? So Q is basically thermoelectric power is of a material, is a measure of magnitude of an induced thermoelectric voltage. Okay, of an induced thermoelectric voltage in response to a temperature. So when we apply temperature difference across the materials, so the thermoelectric voltage that is induced because of the temperature difference, that is measured as Seebeck coefficient, and we have to or the thermo power, and that we have to calculate for T equals 300 Kelvin. So as given in the notes as well, that is given by minus kb upon 2e, the formula to determine. So we will not go into the theory of this. The formula of this is given by this, divided by pi square by 3 T by TF. So here you just have to put all the values in SI unit, and the answer that you will get is minus 0.77 into 10 to the power minus 6. E is the electronic charge. This is the electronic charge. Alright, and all the values are provided here. Electronic charge E is also provided. You just put the values in, and you can find that the value that comes as Q comes as minus 0.77 into 10 to the power minus 6 volt per Kelvin, or you can write it as minus 0.77 microvolt per Kelvin. Alright, that is our Q. And here remember that just to show, okay, what is 1 volt. So 1 volt will come as 1 joule by 1 coulomb. Okay, so you have to write your electronic charge, which is in coulomb, 1% of 18 coulomb, and you will have joule by coulomb, which will be 1 volt. Alright, so this is our Q value that we get from this. And just a quick note now, note that an experiment from experiments. So we can measure this Q for lithium actually comes as 14 microvolt per Kelvin. So you can see that even so the sign the sign of Q for some materials is not correct like lithium, or some materials like for example that we have seen lithium is not correct as obtained from Sommerfeld model from the Sommerfeld model. Also the results vary in magnitude, but the order of voltage, which is in microvolt, which is in microvolt, is correct. Therefore magnitude wise it gives better prediction than Drude model. So we have seen in the lecture note also, you can see that the Drude model would have given a 10 to the power minus 4 volt per Kelvin, but now we are getting microvolt per Kelvin, which is the range in which we get this thermal power Seebeck coefficient. But still, you can see that even the sign is different. So this is not a good method for Sommerfeld model, and so we need some other theory as well. So we will not discuss it in more detail here. Alright, so we are already out of time, I guess. 8 minutes recording. Okay, so let me just stop sharing. Alright, so in today, we are at the end of this session. So in today's sessions, what we did was, first we did this infinite square well symmetric potential problem that was set from our previous session. So we quickly went through again to the theory, and then we finally went through the Python script, and the Python script will be shared with you, so you can again go through the Python script and see how the results are same or different from the infinite square well. But what we saw was that although numerically the results were different a little bit, because like we have like symmetric functions, so we have an odd wave function and even wave function as our solution, but the physics remains the same. Even if we change the output from 0 to a, if we displace it from minus a by 2 to a by 2. And then we did a problem on the two-dimensional electron gas. We calculated the various relation like n versus n and kf relation, and then we also calculated the density of states for the two-dimensional free electron gas. And then we also use the first the Sommerfeld model, and we saw that our chemical potential terms epsilon f, and then we also analytically basically we proved that the Sommerfeld expansion is not correct for two-dimensional free electron gas case. We did it by applying Sommerfeld expansion to the free electron density for the two-dimensional case, and we also actually calculated it analytically as well. And then we did a similar problem for the one-dimensional case, where we just did some relation and the density of states for the 1D free electron gas. And in the last problem we did was a numerical problem. So we see how to use the formulas and find various values from the electron density, like the Fermi energy, Fermi vector, and Fermi velocity, the heat capacity we find, and the sum of power as well. So this is the end of the session, and in the next session we will continue with some similar problem on some more one or two problems maybe on this Sommerfeld model, and then the next week topics. Alright, thank you for your attention.